Hello friends, so this is the first lecture of this course numerical methods, and in this lecture I will talk about errors in numerical computations, and in the later part of the lecture I will introduce system of linear equations. So first of all, let us talk about error. So in the concept of error in numerical analysis, we are having a term significant digits, and that play very important role for the accuracy of any numerical computation. So for example, suppose I want to perform a numerical computation with a real number, let us say x equals to 1 by 3. However, the computers generally stores the finite number of digits. So every computer performs the computation by taking finite number of digits. However, if we see this particular number in decimal format can be written as like this and having the infinite number of digits after decimal. So the computer cannot perform the computation with such infinite long string of digits. So what happen, we need to cut down this number somewhere after some fixed decimal places. So for example, if I cut down this number after 4 decimal places, so this portion after this particular thing will be ignored, and hence we are introducing an error in our computation. If you see here this is a very small error up to 5th place of decimal. However, in further computations this small error propagates and become a large error. So now how to do it? Before that, let us learn how the computer stores the number. So in computer each number can be stored by a fixed length. So fixed length means the fixed number of digits, and it depends on computer that how many digits we can store in the computer. Different computers can have different ability to store the number and to perform the computation with different number of digits. But in general we are having a floating point representation which generally each computer follow, and in this representation each number can be written as plus minus m into 10 raised to power k. If I am talking about decimal number, means numbers having base 10. Here this m is called mantissa and k is an integer. Now the range of this m will depend on the base of the number. So if beta is the base of representation, then this will be for example in decimal representation the range of m will be 0.1 m into up to 1. In fact, this particular representation is called normalized floating point representation. So for example, if I am having a number, let us say 5431, so in floating point form this particular number can be written as 0.5431 into 10 raised to power 4. Similarly, if I am having a number minus 1.23 then this particular number can be written as minus 0.123 into 10 raised to power 1. So, here you can see the mantissa is 0.5431, here mantissa is 0.123 and each one is coming in this range. And then k is 4 here, k is 1 here. Suppose I am having a number 0.0056. So, here you can see that 0.0056 is less than 0.1. So, what will happen? I will write this number as 0.56 into 10 raised to power minus 2. So, this is the floating point representation of a number in the computers, and the digits in mantissa are called significant digits. So, if someone will give you a number and ask you, tell me how many significant digits we are having in this number. So, what you need to do? You need to write the number in the floating point representation, and then the number of digits in the mantissa are called significant digits in the given number. Now, as I told you that computer can perform the computation with finite number of digits. So, after the finite digits, if the number is having more digits, what we need to do? We have to cut down those digits, as I have given an example of 1 by 3, that is 0.3333 and so on, and suppose I have taken only this portion. Now, what will happen? So, there will be some we are introducing some error in our computation by ignoring this part of the number. So, this can be done in two ways. One is either we truncate the number after finite digits, or we perform rounding off of the number. So, here truncation means that we will take this much term and after this whatever we are having we leave out as such. However, rounding off is having a different procedure for cutting down a number after some finite digits. So, let me tell you how we will perform rounding off. So, when a number is rounded to n significant digits, the last retained digit is increased by 1 if the discarded portion is greater than half a digit, and the last retained digit is not changed if the discarded portion is less than half a digit. For instance, rounded to 2 significant digits, the number 0.1251 becomes 0.13, because please note that here the 51 is greater than 50 means this is 0.0051 is greater than 0.005. So, what will happen? If I want to round it off this digit up to 2 significant digits after the decimal, if I want to round off this particular number, then it will become 0.13. Similarly, if you take 0.1249, it becomes 0.12. So, what is happening? If I am having a number x which is having some digits, let us say like this. So, let us say 4 digits, and I want to round it off this number up to 2 significant digits after decimal. So, what will happen? I will see this particular portion. So, if this particular portion is greater than 0.0051, 5, or I will write not 0.005. Then what will happen? This particular number, this particular digit will be increased by 1. If it is less than 0.005, then this particular digit retain as such, no change in this digit. So, for example, I have taken 0.1251. So, here 0.0051. So, this particular digit is greater than half. So, after rounding up to 2 significant digit, it will become 0.13. If I take 0.1249, it will become 0.12. What will happen if it is exactly 0.125 and I want to round up it up to 2 significant digits? So, what will happen? This will retain 0.12, but suppose I am having a number 0.135 and I want to round off this up to 2 significant digit, it will become 0.14. Why I am doing this? This number is same, but here I am not increasing this digit by 1, but here I am increasing this, because if this is the case that in the last you are having exactly half of the number, so what will happen? We will round off the number in such a way that the last digit should be an even digit. For example, should be an even number. For example, here 0.125, so 2 is an even. Here 0.135, here 4 is an even. So, I want to make this even. So, for making this even, I want to increase it by 1. So, this procedure is called rounding up a number up to given significant digits, and this particular thing play a very important role in numerical computation. And basically here we are introducing a very small error in the number by rounding up or truncated it up to some finite number of digit, but later on in the computation it propagates and become a large error. Let us take an example of that. So, consider this particular matrix, and for this matrix, and I want to find out determinant of this by rounding each intermediate calculation up to 2 significant digits. So, I have taken this matrix. Let us calculate the determinant, just 0.12 into 0.13 minus 0.21 into 0.14. So, this particular number become 0.0156 and this particular number become 0.0294. Now, as I told you, I need to round up each intermediate calculation to 2 significant digit. So, when I rounding up it, it will become 0.01516, because here 6 is half of the digit, and so 0.016, this will remain as 0.029, and the finally determinant is minus 0.013. On the other hand, the exact solution is this one minus this one, and it is 0.0138. Now, if I round up the final result up to 2 significant digits, it will become 0.014 and minus 0.014. So, you can see the up to 2 significant digit, the correct solution is minus 0.014. Wherever if I am performing rounding up in the intermediate calculations up to 2 significant digits, it is coming minus 0.013. So, we are having a significant error in the calculation where I am rounding up each intermediate calculation up to 2 significant digits. Now, what type of error we are having in numerical computation? So, the first error can be defined as true value minus approximate value. Approximate value means which we are calculating using the numerical method. So, if I am getting like the true value, exact solution, so error will be 0. Now, the absolute error is called the absolute value of the error. The relative error is a measure of the error in the relation of the size of the true value, and it is given as the absolute value of the error, that is the absolute error upon absolute true value. The percentage error is defined by multiplying multiplying by 100 to the relative error or 100 times of the relative error. The term truncation error is used to denote error which result from approximating a smooth function by truncating its Taylor series representation to a finite number of terms. So, if we take this particular example, here the true value is minus 0.0138, while the approximate solution which we are getting by rounding of each intermediate calculation up to 2 significant digit is minus 0.013. So, the error here is minus 0.0008, absolute error is 0.0008, the relative error is 0.0008 upon 0.0138 and it becomes 0.058. It is looking small, but when we see the percentage error, it is 5.8 because it is 100 times of this particular number, and which is now by looking at the error 5% error, more than 5% error is quite significant. Now, let us talk about significant digits in the approximate solution of approximation of a number. So, let x a be an approximation of a number x, or then we say that x a approximate x to r significant beta digits, where beta is the base of the number, if x minus x a and the absolute value of this difference is less than equals to half times beta raised to power s minus r plus 1, where s is the largest integer such that beta raised to power is less than equals to mod of x. So, let us take some example of it. So, let us say true value is 1 by 3 and the approximate solution is 0.333. Now, I want to check up to how many significant digits this approximate solution is true for the match with the exact solution. So, first of all I will calculate x minus x a and it will be something 0.00033 and so on. Now, if I check this, this is less than equals to basically 0.0005. So, 0.5 into 10 raised to power minus 3, and as I told you it is by the given definition. So, beta is the base, so base is 10 here. Now, s minus r plus 1 equals to minus 3, I got a relation. Now, I want to find out the value of s. As I told you, s is the largest integer such that beta raised to power s less than absolute value of true solution. So, here moreover we can have that 10 raised to power minus 1, that is 1 upon 10.1, which is less than 1 by 3, the true solution. So, this gives me s equals to minus 1. So, from these two equations what I can write, r equals to 3. So, hence I can say that the approximation point 333 is having 3 significant digits to the exact value 1 upon 3 or match with the exact value with 3 significant digits. If we take one more example of the same thing, so for example, I am having true value is 0.02138 and approximation is, let us say, 0.02144. So, here again following the same process, this becomes 0.00006, which is less than 0.0005, or what I can say, which is equals to 1 by 2 into 10 raised to power minus 3. So, again like earlier one, here s minus r plus 1 equals to minus 3. Moreover, here the true value 0.02138 will be greater than 10 raised to power minus 2, that is 0.01. So, here this gives me s equals to minus 2. So, by substituting this value of s here, minus 2 minus r plus 1 equals to minus 3, I got r equals to 2. So, here this approximate x is having 2 significant digit to the true value 0.02138. And let me introduce the introduction to system of linear equations. So, in general we used to see this system of linear equations in a number of applications in science and engineering. Most of the problem in science and engineering can be formulated into nonlinear equations, and that can be approximated into or converted into linear system of linear equations finally to solve the overall system. Now, a linear system of n equations with n unknowns is given as by this type of. So, here this is the first equation, here x1, x2, xn are the unknown variables, a11, a12, a11 or aij are the coefficients in different equations, and b1, b2, bn are the right hand side vector. In the matrix notation we can write this particular system as Ax equals to b. Now, how to solve such a system? So, solving a linear system with n equations and n variables is more difficult when n is greater than equals to 3, because if I am having 2 equations with 2 unknowns, I can solve it directly. But if I am having 3 equations or more than 3 equations in the same number of unknown variables, it becomes quite difficult, and we need some systematic way of solving such system. So, here I want to introduce a direct method that is called Gaussian elimination. So, it is a systemized algorithm or systematic method for solving the system of linear equations having 3 or more variables with the same number of equations. It involves mainly 2 steps. First one is changing coefficient matrix into row echelon form. So, basically coefficient matrix are having the coefficients of unknown variables from different equations, and then finally back substitution. So, let us take an example of 3 by 3 system to explain this particular method, and then we will solve an example of this. So, suppose I am having 3 equations. The first equation is like this. So, 3 equations in 3 unknown. In matrix form I can write it a11, a12, a13, a21, a22, a23, A31, A32, A33 into the unknown vector x1, x2, x3 equals to right hand side vector b1, b2, b3. So, in Gaussian elimination method, what we used to do, first of all we will write the augmented matrix which is given as the coefficient matrix A, and we append the right hand side vector as the last column. So, for example, this is the coefficient matrix here. What I will do, I will append this B1, B2, B3 here. Now, this is my augmented matrix. Now, what I will do, I will perform elementary row operations on this matrix to convert it into row echelon form. So, first of all, to convert it in row echelon form, which is basically I want to make it an upper triangular matrix, something like this. So, first of all I will make this and this particular element 0 with the help of this element. So, if this element is 0, what I will do, I will interchange it with some other row where the first element, the element in the first column is non-zero. So, then after that if I will do this some row operation on this, so first row will not change, so I can do it here itself. So, first row will not change, so I will make these two entities 0 and then these numbers will change. After that what I will do, I will make this particular entity 0 with the help of second row. So, I will make this entity 0, so these two entities will change. Now, if you see this particular thing in the system of linear equations, what I will, from the last row I will be having A33 double prime or double dash equals to into x3 equals to b3 double dash. So, this will give me x3 equals to b3 double dash upon. So, from here I will calculate the value of x3. If I substitute this value of x3 in the second equation, I will get the value of x2, and if I substitute the value of x3 and x2 back into the first equation, I will get the value of x1, and this particular procedure is called Gaussian elimination. So, let us take an example. This particular system of equation, we need to solve the following system using Gaussian elimination on a computer using a floating point representation with 3 digits in the mantissa, and all operations will be rounded. So, I am having 3 equations in 3 unknown. So, augmented matrix for this system is given by this particular 3 by 4 matrix. So, this is the right hand side vector. Now, what I will do, first of all I need to make this and these two entities 0 with the help of first one. So, for that I will use the row operations like R2 is replaced by R2 plus 1.3 upon 0.143 R1, and R3 is replaced by R3 minus 11.2 upon 0.143 R1. We get this particular matrix. So, these two entities are 0, these entities are also changed. Then I will make this particular term 0 with the help of second row. So, I need to perform the operation R3 is replaced by R3 plus 32.3 upon 4.19 R2. From that I will get this one. So, now you can see this particular matrix in a coefficient matrix is an upper triangular matrix. Now, from the third row of this I can say that x3 is 2 upon minus 1, that is minus 2. If I substitute this value of x3 in the second equation, I will get x2 as minus 2.82, and finally, if I substitute the value of x3 and x2 in the first equation, I will get x1 as minus 0.950. However, the exact solution of this system is like this, and you can see we are having huge error in our solution which we obtained using the Gaussian elimination method. Here, as you know, we have put the procedure in a correct manner, but still a big difference in the final solution. So, how to overcome this? This can be done using the Gaussian elimination method using partial pivoting, and that I will introduce in the coming lecture, in the next lecture. So, in this lecture I told you about the errors in numerical computations, what type of errors we are having, what is the concept of significant digits. I have taken some example in which we lose the significant digits in further computations, and finally Gaussian elimination. So, with this I will stop myself. Thank you very much.